Hello everyone. In this video, we are going to see how we can implement dimension analysis using regression model based on computer vision technique. The approach that we have followed for this particular problem statement is that first we are going to acquire the image through a webcam. Then we are going to filter that image into its respective R, G and B components. We are using a value of threshold which is zero point 0.4, and we have come to this value through a heuristic approach. Now, once the image has been segmented, which is basically it has been converted to a two-dimensional image, we are using edge detection through canny edge detector, which is basically an algorithm to detect edges. And now the image is converted into a single dimension image. Basically now the image has been converted from RGB to two dimension by segmentation, and now to a single dimension image by edge detection. Now this single dimension image, which is just zeros and ones basically, can now be given to a function called as region props, which is available in MATLAB, and it helps you to extract features of that particular single dimension image. Now, once we have extracted all the features, and namely we are basically dealing with only four kind of features, which we will see in the code as well. So once the features have been extracted, we are basically calibrating the resolution at several distances. Here for this particular case, we have taken 6 distances, and once we have made a model using those 6 distances and resolution, we are basically creating a regression model, basically, which will try to establish a relationship between the resolution and the distance. Now once we have the model, we can test that model using a test object, and upon testing we can see the efficacy of the model by calculating the mean square error of that particular test. So without further ado, let us go to the MATLAB variant of that. So let me open the MATLAB code for you. Alright. So here in front of you is the MATLAB code. Let me go step by step as to what each particular snippet of this code is doing. Alright. So this part of the program is dealing with the calibration, meaning to say that we are trying to determine the resolution and establish the model. We are basically trying to create the model at this particular stage. So the first step which here is to basically acquire the image. Now once the image has been acquired, we are dissolving that image into its components, which is basically R, G and B, as you can see, and the threshold level of 0.4 has been taken over here. And once that threshold level has basically segmented the image, we are trying to sum all the planes into one particular variable called as isum. This is basically the thresholded image. Alright, and once the image has been thresholded, as I had said earlier, we are basically using an edge detection to determine the edges and also to convert that particular image into a single dimension image called as BW over here. Now this BW variable is the single dimension image, which is ready to be given to the function called as region props, and region props basically works on single dimension images, and we need to provide what features we are interested in those particular objects that have been detected by the function region props. So in this case, the function region props is considering only the features of bounding box, area, convex cell and perimeter. Now why we are using these will be clear in subsequent approaches. So now once this obj basically will be the array which has been returned by region props. Once this is populated, the first thing that we are doing is, for all the objects that have been discovered, we are just using the bounding box, which is actually, as the name suggests, it will basically create a rectangle over the object detected, just in order to give the perspective of how many objects have been detected. And once we have all the objects, because we are interested in only one object, and for the sake of simplicity we are considering the fact that the object of consideration is the one which is having the largest area. So what we are doing here is, in this part, we are basically populating the vector area list with the areas of the objects detected. And once that is done, we are calculating the maximum area and index using the function max, and area list is the vector which is having all the areas of the object detected. So at this stage, you have that particular index of the object and the area as well of the object, which is actually our interest. Right? Now, we are basically drawing a final bounding box over that particular object which is having the largest area. All right. So this part of the code is basically, as I said, that it is going to draw the bounding box over the index. Now this index we have retrieved from the maximum area analogy. Right. Now, since we have to calibrate, we have to do this particular process at several other distances as well. So we need to know the actual length and width of the object that we are using for calibration, and that is basically provided over here. And if you can see from the feed of the camera, which I will provide it in a minute, just a minute. This is basically the object that we are using for calibration. Okay, so as this box over here can give you the live feed of the object that we are considering. So this is basically that object through which we will basically create the model, and then in the subsequent testing phase we will see that how other objects can be tested. So let me first run this and show you as to how what I have explained over here up until now is actually being implemented. Okay. All right. So I've run the code, and okay, up until the time the code gets executed. So the actual length and width is known to us, and through that we are basically calculating the resolution. And how is that resolution coming to us? The function bounding box in its third and fourth parameters returns the length and width in pixels of the object which is under consideration. All right, so we know the actual length and we know the length returned in pixels. So basically we know the resolution. And why have I calculated two resolutions? Because we have two parameters, length and width. So we are calculating the average of the two, and this RAVJ is basically the mean resolution, all right, at a particular distance. So let me just right. So as you have seen that this is our original image, and the second diagram is basically showing us the thresholded image, or which is a two-dimensional, or in other words it is also called as a grayscale image. And the third image that you are seeing is basically edge detected from thresholded image, and this is basically just zeros or ones, or this is a basically single dimension image. Now this third image is the input to region props function, which is drawing all the rectangles. As you can see, there are several other objects also detected in the fourth image. On every object that has been detected, the bounding box has drawn a rectangle. Now what we are doing, since we know for a fact that our object under consideration is the largest amongst the all. This is kind of a simple noise filtration technique. So we have utilized the fact that the largest area is the only area that we have to filter out. And once we are doing that, we are getting a bounding box over the object of our interest, which is represented in green. Now, the calibration part, because up until now, there has the only implication of region props is to actually determine the features of an object or to simply detect an object. So once we have detected an object, the calibration part is quite simple. As you can see that if I were to just type in RAVG, I'm getting 82.0391, which basically means that at this particular distance, the actual resolution which we are getting is 82 pixels per inch. Now, this is the calibration part. Now we have to repeat this process at about other distances, say 12 inches or 24 inches. We have to repeat that. And once we do that, surprisingly, we will see that it all comes under a linear regression. That is evident from the model that we are considering over here. Right? So as you can see, the table has already been populated. We are considering the following distances: 13.1, 15.5, 17.9, 20.3, and so on. And at these distances, we are basically calculating the resolution which is obtained as I have shown you before. Now, the linear regression has to be populated using certain parameters which are obtained by multiplying the distance and the resolution, as is evident from this table. And why we are using linear regression, because this can be a question like why we have used linear regression to implement our modeling. This is evident from the scatter plot of our data. What we are seeing in red dots over here is that our data is basically following a simple line. So which is a clear indication of the fact that we can indeed use linear regression to model our system. So once this system has been implemented, we know the coefficients of our regression, which is basically the values of A and B, which is in this case, A comes out to be about 115 and B comes out to be -3. So now the next step is to basically test this efficacy of the model at different distances. Of course, we will not take the same distance that we have taken in the calibration phase. So without further ado, let us go to the testing part. Wait a minute. All right. Wait a second. So this is the testing phase of the program. And here we would now basically test the model which has been implemented through linear regression. So in order to implement this, we are considering this test object. We have already measured the dimensions, which if it is visible, it is basically 2 inches in diameter. So this is the object under our test. So let me first explain what exactly is going on over here. The initial stages of image segmentation and later on subsequent filtering in order to retrieve the object from this particular image is the same as what it is in the calibration part. Like the first part, you can see that we are first acquiring the image, and which is over here. We are first acquiring the image. This part is basically acquiring the image. Then this part, as already mentioned before, is the segmentation part, as we are mentioning in the title that it is a thresholded test image. When we have thresholded our test image, then we have used the canny operator in order to convert our two-dimensional image into a single-dimensional image, which is necessary in order to implement the feature extraction through region props function. Now, in this case, as was the case in calibration part, if you see, the region props function utilized bounding box area, convex cell, and perimeter kind of properties. But these will not be the this will not be the case in testing phase, because now our area of interest is basically only two features, which are the area of the object detected and convex hull. Convex hull is a new feature over here. What it actually does is it basically draws a convex polygon. Convex polygon basically is wherein the internal angles are all less than 180 degrees. So it basically draws the convex polygon which encloses our object, and it returns all the coordinates of those points, which are basically the vertices of the polygon. It returns them. Now, why is it necessary in this case? Because since we are testing our model, it will be prudent to test it through irregular objects or objects having non-symmetrical dimensions. And that is why convex hull is very helpful in this case, because it returns the coordinates. And using coordinates, we can always do several calculations, like we can compute the area of the polygon enclosed. And polygon is the closest approximation to the object which is being considered in this case. In this case, since it is a circle, so somebody can argue that we can also implement this through bounding box. Bounding box can also draw a rectangle which can enclose this circle. But the argument would be that this circle, if it is not regular, it has some irregularities. So that factor can be taken care by the convex hull feature. So these are the basic features that we are going to consider in this part of our region props method. So all of the objects which are being detected by region props will be categorized into area and convex hull, and this will be stored into the variable called object. So basically obj would be a object that would have two, just like a data structure has two variables inside. So here obj part will have two places which will be dealing with the area and the all the coordinates that will be returned by convex hull feature. So again, in order to filter out all the unnecessary objects that are present in this feature, we would again use the maximum area approach. We would basically only concern ourselves with the maximum area of the objects that has been detected. And once the index of that particular object has been retrieved, which is of maximum area, we are going to populate a list called CH, and that is going to be populated by the feature called convex hull. So CH is basically that particular area, or you can call it as a vector, which will have all the coordinates of the vertices, which are basically vertices of that convex polygon which encloses this object. Right? I have already run this code. So in order to show you, I can just mention CH over here. And as you can see, you are having this set of coordinates over here. So this is basically what convex hull feature does. Right? So once we are having all the coordinates, what we can do is we can basically plot the x and y coordinates. We can plot a simple star. Why is this being done? This is just in order to show the implementation of convex hull, right? So this is basically the x-axis of, the x coordinate of the vertex is basically given by the this parameter, and the y coordinate is being given by this parameter, the second column basically. Once that is done, we are using the line feature to draw a line, and line basically utilizes the x data, which is the first column of ch vector, y data, which is second column of ch vector. And once that is done, we are basically trying to say that the object has been finally enclosed by a polygon. And finally, the area underscore poly, this variable is basically going to tell you the area which has been computed by the poly area feature, which is basically telling you the area in pixels. So for this particular object, if I were to just tell you the area underscore poly, and this, which is basically 21,350 pixels square, right? So now if I were to just tell you, if I were to just show you the actual uh, images over here, right? So as you can see that the first image is the test image. This is the, as I have already said before, that the part up until there, up until the point where we are filtering the objects based upon area, the program is same to the calibration part. So you can see the test image over here, the thresholded test image. This is based on RGB segmentation. And then the edge detected from thresholded test image. This is a single dimension image, which is being input to the region props function. And as mentioned before, the region props function in testing phase is utilizing only two parameters, your area and convexity. Now this figure that you are seeing, the last figure, the blue points are basically stars which are drawn on the vertices which are detected of the polygon which is enclosing this circle. So this is a much better approximation than that of a bounding box. Now this circle could be, as you can see, that this is not an exact circle. The circle could be a little different also. It could be a little irregular. But nevertheless, since we are enclosing it with a polygon, we are having a closer approximation than other methods. And finally, the area which has been computed, and since I have already told you that the actual dimension of this is about 2 inches, so we can do a small calculation in order to implement, in order to show you what exactly is the result telling you. All right, so here we are going to basically calculate the actual dimension of the circle which was in consideration based upon the area which we have got through the convex hull approach. So the area over here tells us that it is about 21,350 pixels square. This is in pixels square. So we first would want to know the actual resolution at this distance. This distance is about 14 inches. And so that, for that we have to go to our model. So as you can see here, this was the implementation of the MATLAB code. So we can say that y is equal to a is, okay, we can first give the variables a. A has come out to be 109.46. B has come out minus 3.025. And now, in order to know the kind of resolution at this particular distance, we have y, which is basically the resolution, that is a plus b times x is our distance, which is 14 inches in this case. So this comes out to be 73.110. We can approximate that to be a 73.1. So basically this is the resolution from the model that we have implemented before, and this, using this, we can come to the conclusion of what exactly the distance dimension is. And of course there are going to be some errors, and we are going to implement a mean square error in order to know as to how true is our model to reality. So say this is the resolution, that it is 73 pixels per inch, and the area which we have got is about 21350, right? So I can just tell this as area to be as 21350, and now we know that the radius is nothing but radius square is nothing but area divided by pi. So area by pi comes out to be this, and this we can basically, or say I basically say this as rad square to be area by pi, and radius to be nothing but a square root of the rad square. This is 82.4373 pixels. Mind you, we are currently only in the pixels domain. We have taken the area in pixels, and that is why we are getting the radius in pixels. Now the only thing which is between the actual radius and this radius is the resolution which we have obtained through the model, right? So that over here is basically in the variable y, right? So I can say that resolve is nothing but y, which is this. So it basically means that this is 73.11 pixels in inch. So 1 pixel would then correspond to 1 over 73.11. So that would be, I can say x is nothing but 1 by resolve. So x comes out to be 0.137. This is what is like what 1 pixel is, right? So we have like this is 73.11 pixels in 1 inch. So 1 pixel then corresponds to 0.137 inches. So our radius, which was 82.4373, so actual radius is nothing but this value of x into your radius in pixels, which comes out to be 1.1276 inches. And that is pretty close because the diameter was 2 inches. The diameter of our object was 2 inches, and so the radius of the object was basically about 1 inch. So the error in this case is about 0.1276 inches, right? So using this, we have then populated the mean square error, because at different distances we have got the error model now, that is in this particular diagram, which is evident. And eventually we have got the mean square error to be 0.3515, which is pretty good, because the closer this mean square error is to 0, the better your model is. So I would end the video over here. Thank you for your time.